Welcome to the Deep Dive, where we unpack complex ideas and really try to extract those golden nuggets of understanding.
That's the goal.
Today, we're diving into a concept that underpins almost every digital service you interact with, yet it's, well, deceptively simple on the surface.
Hmm.
As Douglas Adams, with his characteristic wit, once observed about things that absolutely cannot go wrong. When a thing that cannot possibly go wrong goes wrong, it usually turns out to be impossible to get at or repair.
He had a way with words, didn't he?
He really did. And that, my friends, sets the stage perfectly for the surprisingly intricate world of database replication.
Indeed. Our mission for this deep dive is to truly unpack database replication. What it is, why it's absolutely fundamental to modern resilient systems, and the fascinating, sometimes frustrating complexities that emerge when you try to keep identical copies of data spread across multiple machines.
Okay, so let's start with the big why. Why do we even bother replicating data? What are the driving forces behind making multiple copies of, your precious information?
Well, there are really three primary drivers that make replication indispensable. First, reduced access latency. You want your data geographically close to your users, right?
Right, so things feel fast.
Exactly. So they experience snappy response times, whether they're across the street or across the globe. Second, increased availability.
So if something breaks.
Yeah, if one part of your system inevitably fails, a server crashes, a network cable gets cut. Having copies means your service doesn't just grind to a halt. Users can still access their information.
Got it. Latency, availability. What's the third one?
And third, it's key for increased read throughput. As your application grows and more users are reading data, you can simply add more machines, each with a copy, to handle those read queries. It lets you scale out your ability to serve information.
Okay, so speed, resilience, and scalability. Makes sense. But here's the fundamental challenge, the thing that makes replication a genuinely hard problem, isn't it?
What's that?
If your data never changed, replication would be easy. Just copy it once. Done. The entire difficulty in this field stems from handling changes to that replicated data. How do you keep multiple copies perfectly in sync when they're constantly being updated?
Exactly. That's the crux. That is the absolute core of the challenge. And today, we'll explore three main architectural patterns for tackling those changes: single leader, multi-leader, and leaderless replication.
And I imagine each comes with trade-offs.
Oh, absolutely. Each of these comes with its own unique set of trade-offs, making the choice anything but simple.
Right. Let's start with what you might call the workhorse of replication, single leader replication. It's often referred to as master-slave or primary-secondary. For any listeners, this is likely the model they've encountered most often. How does it fundamentally operate?
Okay, so in a single leader setup, as the name implies, one replica is designated as the leader. Think of it as the central authority for all modifications. All write requests from clients must go to this leader.
Only the leader gets rights. Okay.
Correct. It writes the new data to its own local storage first. Then it sends those data changes to all its followers, the other replicas, which are generally read-only.
And the followers just apply the changes.
Yes. And the crucial part is that the followers apply these changes in the exact same order as the leader did. That order is key.
Ah, okay. And clients, can they read from anywhere?
Clients, on the other hand, have the flexibility to read from either the leader or any of the followers. But that golden rule remains. Rights only ever touch the leader.
So if you're making a change, you're talking to the boss. If you're just looking something up, you can go to any of the copies, spreading the load.
You got it.
This sounds like a ubiquitous pattern. Can you give us a sense of just how widely this is used? Like, where would we see this?
Oh, it's incredibly common. Many traditional relational databases like PostgreSQL and MySQL operate this way. Also, commercial systems like Oracle Data Guard and SQL Server's Always On.
So the big relational players.
Yep. And even some non-relational databases, such as MongoDB and RethinkDB, employ this architecture. Beyond databases, critical distributed systems like message brokers, think Kafka or RabbitMQ.
Ah, okay, even beyond just databases.
Right. They also rely on leader-based replication for their high availability queues. It's truly a foundational pattern in distributed systems.
Now, when that leader sends changes to its followers, does it wait for a confirmation before it tells the client, yep, your write was successful? That seems like a pretty significant design choice.
It absolutely is, and it leads us directly into the fundamental trade-off between synchronous and asynchronous replication.
Okay, synch versus asynch. Let's break that down. Synchronous first.
Right. In synchronous replication, the leader does wait. It waits for at least one follower to confirm it has successfully received and processed the write. before the leader reports success back to the client.
And the benefit there is safety, I assume?
Exactly. It offers a strong guarantee. If the leader were to suddenly fail, there's an up-to-date copy on at least one follower. No data loss from that write.
But there must be a downside. Performance.
Yes, the downside is significant. If that synchronous follower becomes slow or unavailable, the entire write operation for the client blocks. It stalls your application.
Ouch. So you wouldn't make all followers synchronous?
Generally not. This bottleneck often makes it impractical, so you'll often see what's called a semi-synchronous setup.
Asynchronous.
Yeah, where maybe just one follower is synchronous for that durability guarantee,
Right.
and the rest are asynchronous. It's a common compromise.
Okay, that makes sense. And what about fully asynchronous replication? What's the other side of that coin?
With asynchronous replication, the leader sends the message to its followers, but it doesn't wait for a response. It just sends it and hopes for the best, essentially.
So it tells the client success right away.
Immediately. The big advantage here is performance, naturally. The leader can continue processing new writes without being bottlenecked by lagging followers.
But the disadvantage sounds like data loss.
That's the major disadvantage, yes. It's a direct consequence of that speed. If the leader fails before a write has been successfully replicated to any followers, those unreplicated writes are simply lost. Gone.
So the write isn't guaranteed to be durable across the whole system.
Not at all. It's a trade-off for speed.
And we've seen very public incidents where this has caused serious problems. I'm reminded of a notable GitHub incident a few years back.
Ah, yes, the mice will failover issue.
Exactly, where an out-of-date MySQL follower was promoted to become the new leader. Because its internal primary key counter was behind, it ended up reusing some primary keys.
Which then caused inconsistency with other data stores, right?
Yeah.
Leading to data leaks.
Right. The net result was, astonishingly, private user data being disclosed to the wrong accounts. That wasn't just a theoretical problem, that was a very real, very public data integrity failure, directly due to the implications of asynchronous replication and failover.
It's a stark and painful reminder, isn't it? That even what seems like a small configuration choice, the durability guarantee of your rights, can have monumental real-world consequences, impacting privacy and trust.
Absolutely. So, okay, let's shift slightly. If you're bringing a new follower online, how do you even get it up to speed? Data is always changing, so you can't just, copy files like you would a static document, can you?
No, you're right. A simple file copy is prone to inconsistencies because the data is constantly in flux. And locking the entire database during a copy, that would defeat the whole purpose of high availability.
So how do databases handle this live synchronization?
The standard procedure goes something like this. First, you take a consistent snapshot of the leader's database. Databases usually have built-in features for this. It's also critical for backups.
And this happens without locking.
Yes. Crucially, this snapshot is taken without locking the database, ensuring your service remains online. Second, you copy that snapshot over to your new follower machine.
Okay, snapshot copied. Then what?
Finally, the new follower connects to the leader and essentially tells it, hey, I have a copy of the database as of this specific point in time. It identifies that point using something like a log sequence number or maybe bin log coordinates.
Right, like a timestamp or bookmark in the log.
Exactly. It says,
Oh.
send me all the changes that have happened since then.
Yeah.
The leader then streams those missed changes, the follower applies them in order, and once it's caught up, boom, it can seamlessly join the live replication stream.
That makes perfect sense. So what happens when things inevitably go wrong? How do these replicated systems handle node outages? Let's start with a follower failing.
Follower failure is relatively straightforward, actually. Each follower keeps a diligent record of the changes it has successfully received and applied. If it crashes or the network connection is interrupted, it simply reconnects to the leader when it comes back up.
And asks for what it missed.
Precisely. It requests all the changes it missed from its last known point in the log. It then applies them and catches up. That's why followers are often called read replicas. They are fairly resilient when they themselves fail. Catch-up recovery, they call it.
Okay, that sounds pretty robust. So the real challenge must be when the leader itself goes down. How do these systems cope with a leader failure?
Yes. That's where things get much, much trickier. Handling a leader failure, a process known as failover, is a delicate dance. It's not trivial.
What are the steps involved?
It involves several critical steps. First, you have to detect that the leader has indeed failed. This often relies on timeouts, nodes stop responding, and after a set period, they're declared dead.
which can be tricky in itself with network glitches.
Very tricky. Second, you need to choose a new leader. Ideally, this is the replica with the most up-to-date data to minimize data loss. This can be done via an election process among the remaining replicas, or maybe by a dedicated controller node.
Okay, detect failure, choose a new leader, then what?
And third, you have to reconfigure the entire system. That means updating all the clients so they know who the new leader is, and potentially updating the old leader if it ever comes back online, telling it it's no longer the leader. All future rights need to go to the new one.
And what are the classic pitfalls, the things that can spectacularly go wrong during this intricate failover process?
Oh, there are several, and each can have severe consequences. If you're using asynchronous replication, like we discussed,
You might lose data.
exactly. The new leader might not have received all the rights that the old leader processed before it died. Those unreplicated rights are then simply discarded, leading to data loss. This is precisely what happened in that GitHub incident.
Right. What else can go wrong?
Another major pitfall is split brain. This is where, due to miscommunication, maybe a network partition, two nodes both mistakenly believe they are the leader.
Uh-oh. Two bosses.
Yep. If both accept rights, your data will diverge and become corrupted. Some systems try to prevent this by immediately shutting down a node if a split brain is detected, but, well, poorly designed mechanisms can inadvertently shut down both nodes, bringing your whole system down.
Yikes. So data loss, split brain, anything else?
Yeah, the timeout for detection itself is a delicate balancing act. Make it too short, and you get unnecessary failovers during temporary network glitches or maybe just load spikes, causing more disruption than they prevent.
And too long.
Too long, and your recovery time stretches unacceptably. Your service is down for longer.
It sounds like there's no perfect answer.
Exactly. These complexities often lead savvy operations teams to prefer manual failovers, even when automatic options exist, because they want human oversight during such critical moments. They don't always trust the automation.
It's clear there's a lot of hidden complexity here. Now, let's peel back another layer. How does the leader actually send these changes to followers? What are the underlying mechanisms for these replication logs?
Right? How does the information actually flow? There are several different practical approaches used in the wild. The simplest, historically anyway, was statement-based replication.
Statement-based, like sending the SQL itself.
Pretty much. The leader would essentially log and send every single SQL write statement, an insert, an update, a delete to its followers, who would then just re-execute those same statements.
That sounds fragile, like it could easily lead to trouble. What are the big pitfalls of just rerunning SQL statements?
You're right, it breaks down quickly in practice. Think about non-deterministic functions like NFW for the current time, or RAND for random number.
Ah, they'd give different results on different machines.
Exactly. They'll generate different values on each replica.
Mm.
Also, if statements rely on the exact existing state of the database, or maybe on auto-incrementing columns, they need to be executed in the exact same order on all replicas, which is hard to guarantee with concurrent transactions.
And things like triggers.
Yes. And side effects from database triggers or stored procedures can differ if the database state isn't perfectly identical when they run. MySQL, for instance, used this as its primary method before version 5.1, but has since moved away from it as a default due to these exact problems. It switches to row-based if it detects non-determinism now.
Okay, so statement-based has clear limitations. What's another more robust approach?
A very common and robust method is write-ahead log, or WAL shipping.
Wall shipping. Okay, what's that?
This approach taps directly into the database's own internal mechanism for ensuring data integrity. Every database uses a WAL. It's a low-level log of byte changes to disk blocks to make sure changes are durable and can be recovered after a crash.
Right, the journal.
Kind of, yes. With WAL shipping, the leader literally sends this exact internal log to followers. It's almost like cloning the leader's disk block changes, byte by byte.
That sounds incredibly efficient and ensures a perfect copy. It must be identical, but does that tight coupling come with any downsides?
It does. The main disadvantage is that it's extremely tightly coupled to the specific storage engine and, importantly, the database version.
Ah, okay. Why is that a problem?
Because the WAL describes data at such a low-level physical block, changes you're often prevented from running different versions of the database software on your leader and followers. This makes zero downtime upgrades Much harder.
How so?
Well, you can't, for example, easily upgrade your followers to a new version first and then fail over to them without potentially breaking replication, because the wall format might have changed. You're effectively locked into identical environments across the board.
Okay, so we need something that offers more flexibility between versions. Is there a better log format for that?
Yes, and this is where logical or row-based log replication really shines.
Logical replication. How's that different?
This approach decouples the replication log from the storage engine's internal workings by using a higher-level logical log. Instead of raw byte changes on disk, it records a sequence of events describing row-level writes.
Like what kind of events?
For example, row X was inserted with these values, or row Y was updated with these new values, or maybe row Z with this unique ID was deleted. It describes the logical change to the data, not the physical storage change.
That sounds like a significant leap forward in terms of abstraction. What are the key advantages of this logical approach?
Well, the biggest advantage is backward compatibility. It often allows you to run different software versions on your leader and followers because the logical format is designed to be more stable across versions.
Making upgrades easier.
Exactly. Rolling upgrades become far more manageable. It's also significantly easier for external applications to parse. This is incredibly powerful.
Why is that useful?
For something called change data capture, or
Right.
CDC. You can use the replication stream to feed data into, say, a data warehouse, or build custom search indexes, or even synchronize with entirely different systems. MySQL's binlog is a prime example of this logical replication approach when set to row-based format.
Okay, logical replication sounds pretty good, but what if you have truly unique needs, like replicating only a subset of data or meeting very specific custom logic for conflict resolution? What's the most flexible, albeit maybe complex, option?
For those highly customized scenarios, you might turn to trigger-based replication.
Trigger-based, using database triggers.
Exactly. This pushes replication logic up to the application layer effectively. You use database triggers those pieces of code that automatically run when data changes, like an insert, update, delete happens, to log the relevant changes into a separate table, like an audit log.
And then something else reads that table.
Yep. Then external processes that you write read from this custom log table and apply the changes elsewhere, using whatever bespoke logic you need.
So you're essentially building your own replication system on top of the database's built-in features. That sounds like immense power, but I imagine it comes with significant trade-offs.
Exactly. It offers unparalleled flexibility for things like subset replication, just copying certain rows or columns, or cross-database replication, where the source and target schemas aren't identical, or implementing very complex conflict resolution rules. Tools like Oracle Golden Gate or Bucardo for Postgres will often leverage trigger-like mechanisms.
But the downsides?
The trade-offs are real. It typically has greater overheads because it's not optimized right down at the database engine level. It's doing extra work. It's also generally more prone to bugs because you're writing custom code. And while it's not a built-in, fully optimized solution provided by the database vendor, it's a choice you make when the other options simply don't fit your specific niche requirements.
Right. Makes sense.
Oh.
Okay, we've covered the mechanics. Now let's talk about a very real, very painful problem that emerges, particularly with asynchronous replication, the lag problem. This is where eventually isn't quite good enough for your users, right?
Oh, definitely.
When you have many asynchronous followers handling reads, replication lag becomes an unavoidable fact of life.
It absolutely does. This leads us directly to the concept of eventual consistency.
Eventual consistency. Sounds vague.
It is, intentionally so. The core idea is simple. If you were to stop writing data, all your followers would eventually catch up and become consistent with the leader. But that word, eventually, is the key.
How long is eventually?
Well, that's the million-dollar question. In normal operations, lag might be mere milliseconds. Perfectly acceptable. However, under heavy write load, maybe during network interruptions or while recovering from a leader failure, that lag can easily balloon to seconds, minutes, or sometimes even more.
And that's when it starts breaking your application, or at least the user experience.
Precisely. That's when it bites you.
And when that lag becomes significant, it's not just a theoretical problem, it directly impacts the user experience in some really surprising ways. Let's talk about some of the specific anomalies that can pop up. The first one is something we call reading your own rights.
Ah, yes, the classic. This is the scenario. A user submits data, say they post a comment on a social network. That right goes to the leader, gets confirmed.
Okay, they hit post.
Exactly. Immediately after, They reload the page or navigate to view their comment, but their read request gets routed to a lagging follower.
And the comment isn't there yet.
Right. From their perspective, their input just vanished. They see the old version of the page or maybe nothing new at all, and they assume their comment was lost or the site is broken. It's frustrating.
So you need something to prevent that. What's the term?
To prevent this, you need what's called read after write consistency, sometimes called read your writes consistency. It's the guarantee that ensures that once you've successfully written something, your subsequent reads will reflect that write.
So how do you solve that? Do you just force every read to go to the leader? That kind of defeats the purpose of read replicas, doesn't it?
It does, and you usually don't want to do that globally. There are several more pragmatic approaches. One common strategy is to keep track of which specific data a user has recently modified.
Like just the things they edited.
Exactly. And for those specific pieces of data, always route that user's reads to the leader for a short period. For example, a social network might always show a user their own profile page from the leader, but maybe other users' profiles from a follower.
Okay, that makes sense. Any other ways?
Another approach is to store the timestamp of the user's last write. Then, for a brief grace period after that, write maybe a minute. Ensure their reads go to the leader, or make sure the follower they're querying waits until it is caught up to at least that timestamp.
Okay.
And the complexity only grows when you consider cross-device consistency. A user might write on their phone, but then immediately check on their laptop. Now you need some centralized way to track their recent writes across devices and potentially route them to the freshest replica, possibly even across different data centers. It gets complicated fast.
Okay, read your writes consistency. Got it. What's the next anomaly we often see with lag?
Our second example is monotonic reads. This one is about time appearing to go backward, which is incredibly disorienting for a user.
Time going backward. How does that happen?
Imagine a user refreshing a feed page multiple times. Their first request hits a follower that's pretty well caught up, and it shows a new comment.
Okay, they see the new comment.
They refresh again, maybe just a second later, and this time, their request gets routed by the load balancer to a different, more lagging follower. And on that follower, the new comment hasn't arrived yet.
So the comment disappears.
Exactly. From the user's perspective, that new comment mysteriously disappears. It's as if their feed is jumping back in time. They saw something, now it's gone. Very confusing.
Seeing things appear and then vanish is definitely not ideal. How do we ensure monotonic reads, make sure time only moves forward?
The solution here is fairly straightforward conceptually, but requires careful routing. You need to ensure that for any given user, all their read requests consistently go to the same replica.
Always the same follower for the same user.
Right. You could achieve this by, for example, hashing the user ID to consistently select a specific follower for them. If that chosen follower fails, of course, you then need to reroute their queries to a new, consistent replica, potentially causing a brief interruption or needing a replica that's at least as up-to-date.
Okay, stickiness for reads. Makes sense. And the final anomaly you mentioned, consistent prefix reads. This one sounds particularly insidious, hinting at causality.
It can be. This happens when the causal order of events is violated in what the user sees. Imagine a conversation thread. Mr. Poons asks a question, and then Mrs. Cake posts his reply to that question.
Okay, question then answer. Simple causality.
Simple causality. But if, due to replication lag across different followers or maybe different partitions, Mrs. Cake's answer arrives and gets written on a follower before Mr. Poons' original question does.
Someone reading from that follower sees the answer first.
Precisely. An observer reading from that lagging follower sees the answer before the question it's replying to was even asked. This fundamentally violates causality. It makes absolutely no sense to the user.
And you mentioned this is worse in partition databases.
Yes, it's especially problematic in partition databases where different parts of your data might live on completely different sets of machines, and those partitions can have wildly different replication lags. There's no guarantee the question and answer even live on the same partition or replicate at the same speed.
So how do you solve that? Ensure causality is preserved.
To solve it properly, you ideally need to ensure that causally related writes like a question and its direct answer somehow get routed to the same partition so they replicate together. Or you need to employ a more advanced distributed algorithms that explicitly track these causal dependencies, maybe using things like version vectors, which we might touch on later.
Wow. Okay. So the big takeaway here for anyone designing or operating a distributed system is that you have to account for replication lag. You can't just ignore it.
Absolutely not. Pretending asynchronous replication is synchronous, or that eventually means right now, is just a recipe for a bad user experience. Incredibly frustrating bugs, and potentially even subtle forms of data corruption or loss from the user's perspective.
You really need to understand these consistency models, read after write, monotonic reads, consistent prefix reads, and consciously decide which ones your application actually needs and then design for them.
Exactly. And while application code can sometimes attempt to paper over these issues, maybe by adding waits or retries,
It gets messy fast.
it quickly becomes complex, brittle, and really error-prone. This is precisely why stronger consistency guarantees from the database itself are often highly desirable, even if they come with performance trade-offs. Trying to handle distributed consistency purely in application code is a very, very hard path.
Right. The complexity of distributed systems requires a very deliberate consideration of these consistency models right from the start. Okay, we've spent a good amount of time on single leader replication, the workhorse, but that model inherently has a single point of failure, the leader.
Yep, the Achilles heel.
What if we want to allow more than one node to accept writes, increasing our resilience and availability even further? That brings us to multi-leader replication. How is this fundamentally different?
Okay, multi-leader. With multi-leader replication, you move away from that single choke point, that single leader bottleneck. Multiple nodes in your cluster are designated as leaders and can accept writes.
Multiple bosses.
Kind of. And here's the key. Each of these leaders also acts as a follower to the other leaders, replicating its changes to them.
So they all talk to each other.
Exactly. They all send their writes to each other. This eliminates the single point of failure for writes and allows writes to proceed even if one leader goes down or maybe becomes temporarily isolated by a network partition.
That sounds like a significant leap forward in terms of distribution and availability. What are the key scenarios where this distributed approach truly shines? Where would you use multi-leader?
One primary use case, and maybe the most common, is multi-data center operation.
Geographically spread out.
Right. You can deploy a leader in each physical data center. This offers dramatically better write performance for users in that region because their writes are processed locally without that slow cross-data center network latency.
So faster writes for local users. What else?
It also provides superior tolerance to both entire data center outages. If one DC goes dark, others can still accept writes, and also better tolerance to general inter-data center network problems because the asynchronous replication between leaders can hide those delays from the end user.
Makes sense. Are there specific tools for this?
Yeah, you see this in solutions like Tungsten Replicator for MySQL, or BBR, bidirectional replication for PostgreSQL, or Oracle Golden Gate can be configured this way too.
So it's fantastic for geographic distribution and resilience against catastrophic failures. What other scenarios benefit from this multi-leader setup?
Another common application is clients with offline operation.
Offline, like on my phone.
Exactly. Think about calendar apps on your mobile device, or maybe note-taking apps. Your phone or laptop effectively acts as a leader, accepting local writes even when you're offline on a plane or something.
And then it syncs up later.
Yep. Then, when you come back online, it syncs those changes it recorded locally with a central server and maybe your other devices, which are also acting as leaders. CouchDB, for example, is explicitly designed for this kind of peer-to-peer style replication.
Interesting. Any other big ones?
And then, critically, there's collaborative editing. Think Google Docs or Etherpad.
Where multiple people type at once.
Right. Multiple users are concurrently editing the same document. Your changes are applied instantly locally, making it feel responsive, and then they're asynchronously replicated to the other collaborator sessions. This relies on breaking changes down into very small units and, crucially, having incredibly sophisticated conflict resolution.
Conflict resolution. This leads us directly to the biggest, trickiest problem with multi-leader replication, doesn't it?
It absolutely does.
If two users edit the same part of a document, or maybe the same database record, simultaneously on different leaders, what actually happens?
Exactly. This is where you inevitably get a write conflict. In a single leader setup, this wouldn't happen. One write would simply block or maybe abort the transaction, avoiding the conflict altogether because the leader serializes things.
But with multi-leader.
But in multi-leader, both writes are successful locally on their respective leaders. They both get accepted initially. The conflict is only detected asynchronously later when the changes replicate between leaders and the system realizes, uh-oh, two different changes were made to the same thing.
And by then it might be too late to ask the user what they meant.
Often, yes.
Yeah.
And if you try to make conflict detection synchronous-like, have leaders coordinate before accepting a write, you'd completely negate the primary benefits of multi-leader replication, which are that local write performance and high availability. You'd be back to cross-data center delays.
So, okay, conflicts are inevitable if you're not careful. How do you even begin to deal with them? Is there a way to avoid them entirely?
Well, the simplest and often the first thing recommended is conflict avoidance. If you can design your application to ensure that all writes for a particular record or a particular data item always go through the same leader,
Then conflicts just won't happen for that item.
right. For example, you might decide that all writes for a specific user's profile data are always routed to the leader in their designated home data center. If you can guarantee that, then conflicts on that specific data are avoided.
But that sounds fragile. What if the home data center leader fails or the user travels?
Exactly. This strategy breaks down if leaders change due to failover, or if users become mobile and start accessing different data centers. Sooner or later, you often have to confront the reality of concurrent writes hitting different leaders. Avoidance isn't always possible.
So if avoidance isn't possible, then you have to resolve them. What's the ultimate goal when resolving these conflicts, and what are the general approaches?
Okay, resolution. The ultimate goal here is convergent conflict resolution. That's a key term. It means that all replicas, regardless of the order in which they receive the conflicting updates, must eventually arrive at the exact same final value. Everyone has to agree in the end.
Convergence. Okay. How do we achieve that?
There are various methods. A very common but often quite dangerous approach is last write wins, LWW.
Last right wins. Sounds simple.
It is simple. You assign a unique ID, usually just a timestamp, to each write, and when a conflict is detected, the system simply picks the write with the highest timestamp, the last write, and throws the other one away.
Throws it away. That sounds like data loss.
It is. This is dangerously prone to data loss if the writes were truly concurrent, meaning neither user saw the other's change first. It silently discards one user's intention completely, just based on which write happened to get a slightly later timestamp, which might even be due to clock skew.
So LWW is generally bad.
It's risky for anything important. Other approaches include trying to merge the values, maybe concatenating two lists if the field was a list. Or, in systems like CouchDB, the database can explicitly record the conflict, keeping both conflicting versions, and basically punt the problem to the application to resolve later.
So it sounds like application logic often gets dragged into the messy business of resolving these database conflicts anyway.
Yes, very much so. Most multi-leader tools provide hooks or mechanisms for you to plug in custom conflict resolution logic. This logic can run either on write, or maybe a background handler tries to resolve the conflict as soon as it's detected, or on read.
On read, how does that work?
With on-read resolution, the database might return multiple conflicting versions of the data to the application when it's queried. The application then have to look at them, decide how to merge them, and then present the single, consistent view to the user. The database doesn't make the choice.
Okay. And we've seen some famous, almost comical examples of where this has gone wrong, right? Like the old Amazon shopping cart bug.
Ah, yes, where items you remove from your cart would mysteriously reappear later.
Exactly. That was often attributed to conflict resolution logic that perhaps merged by prioritizing additions over deletions, essentially preserving newly added items while silently discarding the intent to remove, if those happen concurrently on different systems.
That's a perfect illustration of the subtle, yet incredibly frustrating implications of getting conflict resolution wrong. It violates user expectations.
Is there research into better ways? Automatic resolution.
Fortunately, yes. There's active research and implementation in areas like conflict-free replicated data types, CRDTs.
CRDTs, what are those?
They're essentially specialized data structures and algorithms, almost like magic math, you could say, that are designed from the ground up to automatically resolve conflicts when multiple people edit the same thing concurrently. They have rules built in so that everyone eventually sees the same sensible outcome without needing manual intervention or complex application code.
Where are they used?
You see them used in systems like the database React 2.0. Similarly, operational transformation, OT, is another set of algorithms famously used in things like Etherpad and Google Docs that enable that kind of real-time collaborative editing by intelligently transforming concurrent changes so they merge correctly.
Okay, so specialized data structures can help. Now, beyond just concurrent edits of the same field, are there more subtle, harder to detect conflicts that multi-leader systems can face? Logical conflicts.
Definitely. Think about a meeting room booking system again. User A books room 101 from 2 p.m. to 3 p.m. on leader alpha. Concurrently, user B books the same room 101 for the same time, 2 p.m. to 3 p.m. on leader beta.
That's a double booking.
Right. Even though they didn't directly edit the same database record, perhaps, maybe they created two separate booking records, they represent a logical conflict that needs to be detected and resolved. This often requires deeper application-aware logic beyond simple field-level merges. The database might not know it's a conflict just by looking at the records.
Okay, so we have multi-leader systems with their conflict resolution challenges. How do these leaders actually communicate with each other? What do the network topologies look like when you have multiple leaders exchanging data?
Good question. There are various replication topologies people use. The most general is probably all-to-all, where every leader sends its writes directly to every other leader. Simple concept.
Everyone talks to everyone. What else?
Other patterns include circular replication, where writes pass through a chain of nodes like A sends to B sends to C sends back to A. Or you might see star tree topologies with maybe a central hub leader that relays changes or some kind of hierarchy.
And do these different topologies introduce their own sets of problems? Like, does the shape of the network matter?
They absolutely do. In circular or scar topologies, the failure of a single node can interrupt the flow of replication for large parts of your system, creating bottlenecks or just stopping updates entirely for some nodes downstream.
So all-to-all is better for fault tolerance.
Generally, yes. All-to-all is more fault-tolerant in that regard. However, it can suffer from a different problem. Messages overtaking each other due to varying network delays between different pairs of leaders.
Overtaking, like a message arrives out of order.
Exactly. This can lead to causality violations. For instance, an UP date to a record might arrive at a replica before the original insert for that data point arrives from a different leader that was slower.
So you try to update something that doesn't exist yet on that replica.
Precisely. This is very similar to the consistent prefix reads problem we discussed earlier in the context of single leader lag. And simply using timestamps isn't always enough to correctly order these events because clocks and distributed systems can easily drift, so later timestamp doesn't always mean happened after in a causal sense.
So even with multi-leader, you still have to be incredibly careful about ordering and causality. It sounds like many systems have inherent limitations here that could surprise you if you're not careful.
That's a crucial caveat. Many multi-leader systems, including some well-known open-source solutions like, say, PostgreSQL BDR in some configurations, or Tungsten Replicator for MySQL, have documented weaknesses or specific configurations needed for proper conflict detection or causal ordering. It's absolutely imperative to read the documentation carefully, understand the guarantees it actually provides, and, most importantly, thoroughly test your specific database setup to ensure it behaves the way you expect for your application's needs. Don't just assume a feature works exactly as you imagine under all failure conditions.
Test, test, test. Got it. All right, let's move on to our final and perhaps most radical replication approach. Leaderless replication. This really flips the script, doesn't it? How does it work without a single leader or even multiple designated leaders orchestrating everything?
Right, leaderless.
Yeah.
In a leaderless system, as the name suggests, there is no single designated leader. Any replica node in the cluster can directly accept writes from clients.
Any node can take a write. How does that work?
The client itself, or sometimes a coordinator node acting on its behalf, sends the write request not just to one node, but to multiple replicas in parallel. Say, it sends the write to 3 different nodes that hold that piece of data.
Okay, sends to multiple.
And the key distinction from multi-leader is that there's generally no strict, globally enforced ordering of writes between different keys. This design choice, which was really popularized by Amazon's Dynamo paper back in the day, has profound implications for availability and how conflicts are handled.
What are some examples of systems like this?
Common examples include databases like React, Cassandra, and Project Voldemort. The Dynamo family, basically.
Okay, so if any replica can accept writes, how does that impact the system's resilience during outages? It sounds incredibly available on the surface.
It dramatically simplifies things for write availability in many ways. Imagine you have, say, N3 replicas for a piece of data. If one of those replicas is temporarily unavailable, maybe it's rebooting or there's a network glitch blocking access to it, the client simply sends the write to all 3 replicas in parallel anyway.
And it doesn't need all 3 to respond.
No. If, for instance, 2 out of the 3 acknowledge the write successfully, the operation is considered successful from the client's perspective. The unavailable replica simply misses that particular write for now. There's no complex leader election or failover process required in the traditional sense for writes to continue. The system just keeps operating with the nodes that are available.
But then, if that unavailable node comes back online later, it's clearly missing data. How does it eventually catch up to the rest of the system? It didn't get the right.
Right, it needs to get consistent again. Two primary mechanisms are typically used to bring stale replicas up to date in these systems. First, there's read repair.
Read repair. The read fixes things.
Kind of. When a client reads data, it often queries multiple nodes in parallel as well. If it gets different responses back, maybe two nodes have version A and one node has an older version B, it detects that inconsistency.
Mm.
The client, or coordinator, can then immediately write the newer, correct value, version A, back to the stale replica, the one with version B.
Ah, so the act of reading triggers a write back to fix inconsistency.
Exactly. This is highly effective for frequently read data, as the inconsistency gets corrected quickly.
But what about data that's rarely read?
Good point. For that, there's usually a second mechanism, an anti-entropy process. This is a background process that runs continuously or periodically and systematically compares data between replicas looking for differences and then copies any missing or divergent data across. Think of it like a background synchronization job. This is crucial for ensuring rarely read values eventually converge, as read repair alone wouldn't cover them.
Okay, read repair and anti-entropy. Now this brings us to a core concept in leaderless systems, quorums for reading and writing. How do these quorums work, and how do they ensure some level of consistency without a leader?
Right, quorums are absolutely central to how these systems provide tunable consistency. The idea is this. If you have n total replicas for a piece of data, let's say n to 3 again, a write operation is considered successful if at least W nodes acknowledge it, W for write.
Okay, W nodes must say got it for a write.
Correct. Similarly, a read operation must successfully query at least R nodes, R for read.
And R nodes must respond for a read.
Yep. Now, the crucial condition for ensuring that you typically get an up-to-date value during a read is if the numbers you choose for W and R satisfy this little equation. W plus Rn.
W plus Rn. Write quorum plus read quorum is greater than the total number of replicas. Why is that important?
Because when this condition holds, the set of nodes involved in any successful write, the W nodes, and the set of nodes involved in any subsequent successful read, the R nodes, must overlap by at least one node.
Ah, so the read is guaranteed to talk to at least one node that saw the latest successful write.
Exactly. Since W plus R is bigger than N, there's no way to choose W nodes and R nodes from the total N without having at least one node in common. This ensures that the read quorum includes at least one node likely holding the most recent value written by the write quorum. This is known as quorum consistency.
So W and R are essentially the minimum votes needed for an operation to be considered valid and, well, reasonably consistent. What's a common configuration for these values in practice, like for N3?
A very common choice, especially for balancing fault tolerance and consistency, is to make an odd number, say 3 or 5, and then set W and R both equal to N plus 1, 2, basically a majority.
So for N3, that would be W2 and R2.
Exactly. W2, R2, 2 plus 2 is 4, which is greater than N3. This setup allows your system to tolerate the failure of any one node, since you only need 2 out of 3 for reads and writes, while still maintaining that quorum consistency guarantee, W plus Rn.
And if N5?
If N5, you might choose W3 and RO3. Again, 3 plus 3 is 6, which is greater than N5. This would tolerate 2 unavailable nodes. It provides a configurable knob to balance consistency strength versus availability during failures.
Okay, that seems like a pretty strong guarantee, especially that W plus Rn rule ensuring overlap. Does this always guarantee absolute strong consistency in every single edge case? Like, am I guaranteed to read the very latest write?
Unfortunately, no. It's a strong probabilistic guarantee, but not an absolute one in all scenarios. Even with the W plus Rn quorum rule satisfied, there are still critical edge cases where stale or inconsistent values can be returned.
Like what? What can break the quorum guarantee?
Think about scenarios like complex network partitions that might temporarily split your quorum in weird ways, or maybe a node coming back online with older data that somehow wasn't fully repaired by anti-entropy yet, or truly concurrent writes happening where the underlying conflict resolution mechanism, like the dreaded last write wins we talked about, might silently discard data even within the quorum, or even just plain unlucky timing where a write has been acknowledged by W nodes but hasn't finished propagating to the R nodes involved in an immediately following read before the read completes.
Okay, so it's more about making stale reads unlikely rather than impossible.
It's exactly. Dynamo-style databases are generally optimized for use cases that can tolerate eventual consistency. They prioritize availability, especially write availability. They typically do not provide the stronger guarantees like read after write, monotonic reads, or consistent prefix reads out of the box. unless you implement additional, often complex mechanisms either in the database configuration or at the application level. Those guarantees we discussed earlier are often sacrificed.
So even with quorums, you're not entirely out of the woods regarding consistency anomalies. This sounds like it could be difficult to operate confidently. How do you even monitor data staleness in a leaderless system if there's no fixed order of rights or a single leader's log to track?
That's a really good point. It's significantly harder than in leader-based systems where you can often get a clear replication lag metric by just comparing log positions. In leaderless systems, there's no single point of truth or fixed order.
So how do you know how eventually is?
It's tough.
Yeah.
If a database relies heavily on read repair, for instance, a rarely read value sitting on a stale replica could literally be days or weeks out of date without anyone noticing until it's read. Quantifying eventual becomes a very real operational challenge. It often requires careful monitoring of the anti-entropy processes, maybe sampling data consistency, and often using custom tooling to truly get a handle on the consistency state of your data across the cluster. You have to actively measure it.
Okay. And what about these terms I've heard mentioned in relation to systems like Cassandra, sloppy quorums, and hinted handoff? They sound a bit, well, sloppy. Are they related to this?
They are, and yes, the name is indicative. They are techniques used to prioritize availability even further, potentially at the cost of the W plus RN consistency guarantee during failures.
Okay. How does a sloppy quorum work?
Imagine a network interruption, maybe between data centers, that prevents a client from reaching enough of the home nodes, the nodes that are normally designated to store a particular piece of data to achieve a strict quorum of W.
So the write would normally fail?
With a strict quorum, yes. But with a sloppy quorum, the system says, okay, I can't reach enough home nodes, but I can reach W other nodes in the cluster. I'll accept the write on those nodes instead.
So it accepts the write on any W reachable nodes, even if they aren't the designated owners.
Exactly. This dramatically increases write availability during network partitions. The write succeeds even if the target nodes are unreachable.
But the data is now in the wrong place temporarily. What happens then?
That's where hinted handoff comes in. The nodes that accepted the write sloppily store a hint saying, this write actually belongs to node X. Once the network partition is resolved and node X becomes reachable again, the node holding the hint automatically sends, or hands off, the write data to its proper home node, node X.
So by accepting writes to any reachable nodes, you're essentially saying, I'll take whatever I can get to ensure the write goes through, even if it means that data isn't immediately where it's supposed to be or readable by a normal quorum.
Precisely. It's a big trade-off. You gain extreme write availability, but you explicitly sacrifice the immediate consistency guarantee of W plus RN. A read targeting the home nodes might get stale data until that hinted handoff completes.
When would you use something like that? It sounds risky.
It is a big compromise, but it can be absolutely essential in certain scenarios, particularly for highly available systems dealing with high churn data, where immediate consistency is less critical than ensuring the write always succeeds no matter what. Think about maybe IoT sensor data streams, or perhaps temporary user session information where you can tolerate brief inconsistencies for the sake of extreme availability. React, I believe, uses sloppy quorums by default, while systems like Cassandra and Voldemort often make them optional settings you can turn on if you need that extra availability boost.
Right. And leaderless replication, partly because of this tolerance for network issues, is also particularly well suited for multi-data center operations, similar to multi-leader.
Yes, very much so. Systems like Cassandra and React are often deployed with their nodes spread across multiple physical data centers, treating all nodes across all DCs as part of the overall Erlang replicas for a piece of data.
How do quorums work across data centers?
Typically, writes are sent to nodes in all data centers, but clients often only wait for acknowledgments from a quorum within their local data center, like locale quorum in Cassandra, to keep latency low. The replication to other data centers happens asynchronously in the background. This inherent design handles cross-data center network issues and potential conflicts perhaps more gracefully than some other approaches, as it's built for partition tolerance.
Okay. We've talked quite a bit about how concurrent writes inevitably lead to conflicts. This was a central issue in multi-leader, and it's certainly here in leaderless systems too, maybe even more so. What's the core problem again, and how do we detect these concurrent writes without a single point of order?
Right, the core problem is this. With multiple clients potentially writing simultaneously to different replicas and no single leader enforcing an order, different replica nodes can receive write events for the same data item in different orders due to network delays or partitions.
So node A sees write 1, then write 2. Node B sees write 2, then write 1.
Exactly. If each node simply overwrites the previous value based on when it received the write, you'll end up with different permanently inconsistent final values on different replicas. Node A ends up with value 2, node B ends up with value 1. They've diverged. So they need a way to first detect that these writes are indeed concurrent, not just one overwriting another causally, and second, converge in a single consistent state across all replicas.
And what's the common, but as we've established, often dangerous approach to convergence here?
That would again be last write wins, LWW, which is famously Cassandra's default conflict resolution strategy. It simply aims to discard all but the most recent write, typically determined by comparing a timestamp embedded in the write operation itself.
And the danger is silent data loss.
The immense danger, yes, is that if writes are truly concurrent, meaning neither causally depends on the other, or if there's even slight clock skew between the servers generating those timestamps, LWW will silently discard data. It arbitrarily chooses one winner based on a potentially meaningless timestamp comparison and throws away the other user's intent. It's only really safe if your keys are immutable, never updated, only created, or if you can guarantee that every write uses a unique key, ensuring no concurrent updates to the same key can never happen. For critical business data where updates matter, LWW is almost always a poor choice, which drives the need for more complex but safer solutions like CRDTs or application-level merges we touched on.
Okay, this idea of happens before seems crucial here for distinguishing concurrent writes from simple overwrites. Can you remind us what exactly that means in this distributed context and how it helps define concurrent?
Yeah, happens before is key. Instead of thinking of it as strict physical wall clock time, which is unreliable in distributed systems due to clock skew, imagine it as a chain of cause and effect. Operation A happens before Operation B if B somehow knows about A, or depends on A, or explicitly builds upon A.
Can you give an example?
Sure, if I write a comment on your blog post, and you then write a reply specifically to my comment, your reply causally depends on my comment existing. Your write happens after mine in this causal sense.
Okay, there's a dependency.
Right. If, however, we both simultaneously add different items to the same shared online shopping cart, without seeing each other's actions first, those are concurrent operations. Neither happens before the other because there's no causal link or shared knowledge between our actions before they hit the server. It's about knowledge and dependency, not necessarily about whether the packets overlapped in flight.
That's a great distinction, causality, not just time. So how do systems actually capture this happens before relationship internally to decide if writes are concurrent or if one simply superseded another causally? Can you walk us through that shopping cart example again, but focusing on how the system tracks it?
Okay, let's use that shopping cart again. Imagine the server doesn't just store the list of items in the cart. Every time the cart is successfully modified, the server also assigns a new version number, or a more complex version vector, as we'll see, to the state of the cart, and stores that version identifier alongside the cart data.
So each state has a version.
Yep. Now, when a client reads the cart, the server returns not just the items, but also the latest version identifier it knows about for that cart.
Okay, the client gets the data and the version.
Now, when that client wants to write an update, say add more items, it must include the version identifier it last read, along with its write request.
Sends back the version it saw.
Huh.
Why?
The server then uses this incoming version identifier from the client. If the client's version identifier perfectly matches the server's current version identifier for that cart, it means no one else has modified the cart since this client read it. It's a simple causal overwrite. The server performs the update and generates a new version identifier.
Okay, that's the simple case. What if the versions don't match?
If the client sends back a version identifier that is older than what the server currently has, or the server has multiple versions the client doesn't seem to know about, it implies that another write happened concurrently or since the client last read. The client's basis for its write is stale or incomplete. In this case, a sophisticated leaderless system doesn't just overwrite. Instead, it keeps both the incoming change and the existing changes as concurrent siblings. It recognizes they represent parallel lines of history.
So the server isn't just overwriting, it's actively tracking these different paths of edits by keeping these siblings around. But if it's keeping these concurrent siblings, that means the client now has to deal with them, right? That sounds like more complexity pushed back to the application.
Precisely. This approach, often using version vectors, ensures that no data is silently dropped due to concurrency. It preserves all user intentions by keeping the siblings. However, it absolutely shifts the burden. The client application, on its next read, now receives these multiple siblings, multiple concurrent versions of the same piece of data, and it must have logic to merge them into a single, sensible state.
So we're back to the same conflict resolution problem we saw in multi-leader, but now it's explicitly the client's job.
Often, yes. It's shifted to the client or application layer. The application has to look at the siblings and decide on the final state. A simple but lossy merge strategy might be LWW based on timestamps. A more intelligent merge, like taking the union of items added to a shopping cart from different siblings, is typically needed for better results. The database preserves the history, the application resolves it.
And what if you want to allow deletions in this model? Does that complicate the merge even more, especially with unions?
Yes, significantly. If you just take the simple union of items from concurrent siblings, a deleted item can mysteriously reappear. Why? Because one sibling might represent the state before the deletion, still containing the item, and the other sibling represents the state after a concurrent addition, and the union includes everything from both.
So the delete gets lost in the merge. How do you prevent that?
To prevent this, leaderless systems that support proper merging often use tombstones. These are special markers that explicitly indicate an item was deleted at a certain version. These tombstones are replicated just like any other write or sibling value, and are then considered during the merge process to ensure that deleted items stay deleted, effectively overriding additions from concurrent siblings that happened before the delete in the causal history.
Tombstones for deletions. Got it.
And this is again where those conflict-free replicated data types, CRDTs, become so powerful. They are specifically designed data structures that inherently know how to handle additions, removals, and other operations in a way that automatically guarantees convergence and proper handling of things like deletions without needing complex manual merge logic in the application. They bake the merge rules right into the data type.
Okay. And all of this sophisticated tracking of concurrent edits and causality, especially across multiple leaderless replicas, often builds on the more general idea of version vectors, not just single version numbers. Can you explain those?
Right. For multiple leaderless replicas interacting, a single version number per data item isn't enough to capture the full picture of concurrency. You need a version number per replica, per key.
A counter for each replica involved?
Essentially, yes. Each replica maintains a counter for itself. When it processes a write for a key, it increments its own counter for that key. It also keeps track of the counter values it has seen from other replicas for that key. This collection of counters, replica A count, replica B count, replica C count, forms a version vector.
And how is this vector used?
This vector is sent along with reads and writes. When a server receives a write with a version vector, it can compare it to the vector it currently holds for that key. This comparison allows the database to precisely distinguish between simple overwrites, where the incoming vector clearly dominates or causally follows the stored vector, and truly concurrent writes, where neither vector dominates the other, meaning each replica has seen updates the other hasn't.
So it's a much more precise way to track causality.
Exactly. It ensures safe read-write operations across different replicas without silent data loss due to concurrency, as long as those detected concurrent siblings are properly merged eventually, either by the client or maybe using CRDTs. It's the distributed systems way of encoding and reasoning about the happens before relationship across a potentially sprawling, leaderless landscape where there's no central coordinator. It's related to the concept of vector clocks in distributed systems theory.
Wow. Okay. This deep dive into database replication has truly shown us how incredibly complex the world beneath our apparently simple applications really is. It's fascinating.
Isn't it just?
We started with the foundational need for replication speed, resilience, scale. And then we really dug into the intricacies of the three main approaches: single leader, multi-leader, and leaderless.
And unpack their unique trade-offs along the way.
Absolutely. From the very real dangers of replication lag in single leader systems and those consistency anomalies like reading your own writes or seeing time go backward,
to the subtle art and significant challenge of conflict resolution when you have multiple leaders or leaderless nodes trying to modify the same data simultaneously.
it's become crystal clear that every single design choice here comes with a significant set of compromises. There's no silver bullet.
It really emphasizes that replication is far from a solved or simple problem. It requires meticulous, careful thought about concurrency, about fault tolerance, and about the real-world consequences for your users when things inevitably go wrong or get delayed.
And understanding concepts like eventual consistency, what it really means, and monotonic reads, and that fundamental challenge of ensuring consistent prefix reads, preserving causality across distributed systems. It's just vital for application designers to avoid creating surprising and often deeply frustrating user experiences.
Totally agree. It's not just about getting the data copied from A to B. It's about making sure that copy makes sense in context, maintains integrity, and meets the user's expectations, even under failure conditions.
And the journey to truly robust, truly scalable systems only continues, doesn't it? When we start asking, what happens when our data sets get so big they can't even fit on one machine anymore? How do we divide and conquer our data across many nodes?
Partitioning, sharding.
Exactly. And maybe even more profoundly, how do we get multiple independent computers to actually agree on critical decisions, like who the leader is, or whether a transaction committed, especially when network failures are just a fact of life?
Consensus algorithms. Yeah.
That, my friends, is a whole other fascinating rabbit hole, partitioning and consensus, that maybe we'll explore in our next deep dive.